Hello, I'm Yizhi Huang from Tsinghua University. Thank you for listening to this talk. This talk is about our work, range avoidance, remote point, and hard partial truth table via satisfying pairs. This is a joint work with Yeyuan Chen, who is from Xi'an Jiaotong University and is going to University of Michigan to start his PhD study this year. And Jiatu Li, who is also from Tsinghua and is going to MIT for PhD. And Hanlin, who is a PhD student at the University of Oxford. Today, I'll focus on range avoidance, briefly mention remote point, and not discuss hard partial truth table. For results about hard partial truth table, please refer to Hanlin's talk at Simons Institute. This slide is also based on earlier slides of Hanlin and is modified by Jiatu. So I'll start with explicit constructions. One example of explicit construction is proving circular bounds. Let C be a circuit class, such as AC0. Proving a circular bound against C is essentially finding explicit functions that require a large C circuit. When C consists of general circuit, this is a difficult task, as the best known size lower bound is only 3.1 n. Also, it is still open whether there is a function in e to the np that requires circuit of size larger than 10 times n to compute. E to the np means exponential time with an np oracle. In contrast, Chen proved in the 1950s that almost all Boolean functions require exponential large circuit to compute. This is proved by an e-decounting argument. The number of Boolean functions from n bits to 1 bit is 2 to the 2 to the n, but the number of circuits of size 2 to the n over 10 is only 2 to the 2 to the n over 5, which is much smaller than 2 to the 2 to the n. Therefore, a random function requires exponential size circuits to compute with high probability. However, we don't know how to find such a function deterministically. This is like finding a hay, not even a needle in a haystack, but we don't know how to. Circular bound is not the only example of finding a hay in a haystack. We know that a random binary linear code has super good distance. We know that a random graph has neither large cliques nor large independent sets, and such a graph is called Ramsey graph. We also know that a random matrix is far from being low rank, and such a matrix is called a rigid matrix. But we don't know how to deterministically construct any of these three. In this work, we consider an explicit construction problem called range avoidance. The input to this problem is a circuit C, which is multi-output, and its output length is greater than input length. Any string that is not in the range of C is an acceptable output for this problem. That is, the goal is to find a non-output of C. Apparently, a trivial randomized algorithm that just outputs the random Y succeeds with high probability. So the question is, are there deterministic algorithms for range avoidance? Such an algorithm will be very interesting, as it is showed by Oliver Colton in 2021 that deterministic algorithm for range avoidance implies solution to every explicit construction problem I mentioned before. Following the paradigm of circuit complexity, we can also consider a weaker version of the problem, where the input circuit is from a restricted class, such as NC0. Actually, it has been shown that constructing rigid matrices and good codes can be reduced to the range avoidance problem for weak classes, say NC0. Similarly, we define an average case analog of range avoidance called remote point problem. The input is also a multi-output circuit C. But the difference here is that the output is any string that is far from the range of C. So there is still a trivial randomized algorithm. And the question is still, is there any deterministic algorithm? Actually, the problem is hard even for circuits consisting of only a single layer of XOR gates. Noga Allen, Rina Panigrai, and Sergei Yakovlevich designed a polynomial time algorithm when epsilon is log n over n. However, we want epsilon to be a constant or even close to 1/2 for interesting applications. Here we introduce a conditional upper bound for range avoidance. In the same work by Corton, he showed an FP to the NP algorithm for range avoidance at remote points, assuming an exponential lower bound for e to the NP. And the direct corollary is, under the same assumptions, good binary linear codes, Ramsey graphs, rigid matrices, etc., can be constructed in deterministically polynomial time with an NP oracle. So a natural question is, can we solve range avoidance and remote point in FP to the NP unconditionally, at least for restricted circuits? Our answer is yes, at least for the restricted circuit class of ACC0. In this work, we propose a framework that solves range avoidance, remote point, and hard partial truth table, which I didn't define here, in FP to the NP, using better than trivial algorithms for satisfying pairs, which is a problem I will define later. And here, FP to the NP means polynomial time with an NP oracle. In addition, there are such better than trivial algorithms for satisfying pairs of ACC0 circuit. So we obtain unconditional FP to the NP algorithm for the range avoidance, remote point, and hard partial truth stable problem restricted to ACC0 circuit. The exact definition of this ACC0 is not important here. This framework is an analog of the algorithmic method in circuit complexity, which I will discuss now. In 2011, Brian Williams proved the breakthrough result that non-deterministically exponential time is not contained in ACC0. The proof has the following two steps. First, he showed that a problem called CAPP, which I will define soon, for ACC0 admits a non-trivial algorithm. Then he showed that such an algorithm implies circular bound. CAPP here stands for circuit acceptance probability problem. The input to the problem is a circuit, and the output is an estimation of the acceptance probability of C. That is the probability that C of X equals 1 over all X within some additive error, say 1 over 6. Apparently, the problem has a trivial polynomial time randomized algorithm by just sampling the inputs for enough time. It also has a trivial 2 to the n times poly n time deterministic algorithm by enumerating over all possible X. So here, by non-trivial algorithm, we mean an algorithm that is n times small omega 1 times faster than the trivial deterministic one. Actually, Williams showed that for any typical circuit class C, if there is a non-trivial algorithm for CAPP restricted to C, then there is a lower bound for non-deterministic exponential time against C. For the purpose of this talk, we consider a lower bound for e to the NP instead of NEXP. Now I claim that circular lower bound is just range avoidance for a specific circuit, the truth table generator. So the truth table generator for ACC0 is a circuit that takes the description of an ACC0 circuit C as input and outputs the truth table of the circuit C. We can reformulate the circular lower bound e to the NP not contained in ACC0 as an unconditional FP to the NP algorithm for range avoidance of this specific circuit TT ACC0. To see this, note that such a lower bound roughly means that we can generate a truth table that is hard for ACC0, which is a non-output for the truth table generator in exponential time with an NP oracle. Also, since the truth table generator has exponential size, such an exponential time algorithm becomes a polynomial time algorithm for range avoidance. With this observation, it is natural to ask, is there anything special about the truth table generator? And what about other instances of avoid? In the last year, a work by Hanlin, Rahul Santhanam, and Zhikun Wang generalized the algorithmic method to range avoidance. They showed that non-trivial algorithm for a problem called Hamming weight estimation implies FP to the NP algorithm for range avoidance. Hamming weight estimation is a problem that, given a circuit C and a string at X as inputs, estimate the Hamming weight of C of X. The problem allows pre-processing for the circuit C, but the details of pre-processing is not important here. One can note that CAPP is just Hamming weight estimation for the truth table generator. Therefore, this result generalizes Williams' algorithmic method. Unfortunately, Hamming weight estimation is a difficult problem, and RSW didn't have good unconditional results. But in our work, we showed that if we have non-trivial algorithms for another problem called satisfying pairs, we will have FP to the NP algorithms for range avoidance. The input to the satisfying pairs algorithm consists of n circuits C1 to Cn and m inputs x1 to xn. And the goal is to estimate the number of pairs ij such that Ci of xj is 1, hence the name satisfying pairs. For example, in this table on the left, the number to estimate is 8, as there are 8 1 here. By non-trivial, we mean an algorithm that runs in n times m over log to the small omega 1 n times n time. One can note that CAPP can be transformed into satisfying pairs with 2 to the n over 2 circuits and 2 to the n over 2 inputs. To see this, for a length n input, we can hardcode the first n over 2 bits into the circuit. We can also restrict the problems to ACC0 circuits. And in addition, we already have non-trivial algorithm for ACC0 satisfying pairs. Therefore, we have an FP to the NP algorithm for ACC0 avoid. This result recovers the best known ACC0 circular bounds by Lijie Chen, Xinlu, and Ryan Williams. Similarly, we consider average case circular bounds. This can be reformulated as an FP to the NP algorithm for a remote point of the truth table generator. Note that a truth table that is average case hard for an ACC0 circuit is by definition far from any output of the ACC0 truth table generator. We also showed that non-trivial satisfying pair algorithm for circuit class C imply FP to the NP algorithm for C remote point. The output length of the circuit is required to be much larger than the input length here, due to the parameters of satisfying pairs algorithm we have. And the remoteness we could obtain is 1/2 minus 1 over polynomial n, which corresponds to strong average case lower bounds. The direct corollary here is we have an FP to the NP algorithm for ACC0 remote point problem, with parameters sufficient to recover the best known strong average case lower bound for e to the NP in COW20. Now I'll do a very raw technical overview. For range avoidance, suppose the input is a circuit C. For any language L in non-deterministic time T, we consider a rectangular PCPP for L. Here, PCPP stands for probabilistically checkable proof of proximity. You can just think of it as a PCP. And rectangular means that, first, the proof is a matrix. And second, the queries are generated rectangularly, which means that the random seeds for generating the row indices and the column indices are independent. We define a proof to be an eddy witness if it is of such a form here. The ith row corresponds to some string xi, and the jth column corresponds to cj, which is the jth output bit of the circuit C. So the ijth entry is the jth output bit of C of xi. The intuition for defining eddy witness here is that if we find a witness that is not eddy, then one of its row must be a non-output of the circuit C. Now we consider the PCPP verification. Suppose D is the decision circuit. For every query, we sample the row index I with the row seed and the column index J with the column seed. Then for an eddy witness, whether a query returns 1 is equivalent to whether Cj of x1 is 1. Therefore, estimating the acceptance probability of eddy witness can be modeled as a satisfying pair problem. Now, with the non-trivial algorithm for satisfying pairs, for input with eddy witness, we can obtain a speed up when non-deterministically deciding whether the input is in L. But from a non-deterministic time hierarchy, we can find the language L such that not all inputs in L can have such a speed up. This means that there is an input in L without an eddy witness. And recall that hard witnesses contains a non-output. And we can find such a non-output with an NP oracle. Therefore, we have an FP to the NP algorithm for range avoidance. The idea for remote point is similar. We define eddy witness to be any proof matrix that is close to the 4. This is the difference. And to accommodate this change, we need the PCPP to have another property called smoothness. Smoothness roughly means that each entry is queried with equal probability. And this allows the PCPP system to tolerate some error in the proof. Now, with such definition of easy witness, a hard witness will contain a remote point. The remoteness we have is constant, but we can amplify it to 1/2 minus 1 over polynomial n with an XOR lemma in COW20. Now let me summarize this talk. As an analog of the algorithmic method in circuit complexity, we solve range avoidance, remote point, and hard partial truth table in FP to the NP, assuming better than trivial algorithm for satisfying pairs. Moreover, we have better than trivial algorithms for ACC0 satisfying pairs. And therefore, we obtain unconditional FP to the NP algorithms for these problems restricted to ACC0. I also want to mention 2 related open problems. The first is about applications. All known applications of these results here are about hard truth tables and circular bounds. Can we use these results to solve some concrete explicit construction problems, such as Ramsey graphs? The second open question is, can we have unconditional results for stronger circuit classes or with stronger parameters? We don't know non-trivial algorithms for satisfying pairs of stronger circuit classes. Besides, the parameter of the ACC0 satisfying pairs algorithm we have only gives us algorithms with quasi-polynomial stretch. And we want to know whether the stretch can be made smaller. So this is the end. Thank you for listening to this talk.